Lesson 2.6 is on solving compound inequalities. So in this lesson, we're going to be seeing inequalities that have multiple parts to it. So far, we have seen simple inequalities. When two simple inequalities are combined into one statement by the words and, or, the result is a compound inequality. So, we're going to have two inequality statements that are combined with the word and, or. So some examples here, all real numbers greater than 2 and less than 6. So any number that satisfies those two conditions would be included in the solution set. So x is greater than 2, x is less than 6. So x is in between 2 and 6. So the graph would look like this. We'd have an open dot on 2 and 6 because they're strictly, they're not equal to, and then shaded in the middle. All real numbers greater than or equal to 2 and less than or equal to 2. So again, this time we have the equal to part, so the dots would be filled in. Then we have statements with or, so all real numbers less than 2 or greater than 6. So less than 2 or greater than 6, we kind of have two ends here. So any number smaller than 2 goes to the left, any number greater than 6 goes to the right, and those are open dots. The last one has the equal to, so the dots would be filled in. So and statements are kind of joined together, a section that's joined together, and then or statements are something shaded to the left, something shaded to the right. So we're going to look at example 1. It says a water analysis recommends that the pH level of a swimming pool water be between 7.2 and 7.6 inclusive. Write a compound inequality to show the pH levels that are within the recommended range. Graph the solutions. Inclusive means that the numbers 7.2 and 7.6 are included in the solution. So we'll use solid circles, closed dots for our graph, but then we also have that equal to when we create our inequality. So P is going to be the pH level of the swimming pool. So we know that it's going to have to be between 7.2, so it's greater than that, or equal to, because inclusive, P, which is less than or equal to the other endpoint, 7.6. Okay, so that would be our inequality. You could also see it written like this. P is greater than or equal to 7.2, and P is less than or equal to 7.6. Okay, those would be two different ways to write that. And when we put a dot on 7.2 and 7.6, closed dot because we have the equal to, it's inclusive, includes those solutions, and then shade between those two values. There is a try it problem. It says the free chlorine level in a pool should be between 1.0 and 3.0 parts per million inclusive. Write a compound inequality to show the levels that are within this range. Graph the solutions. So go ahead, pause the video, and try this problem on your own. So the inequality, we would have 1.0. Inclusive meant the solutions included, so less than or equal to x, which is less than or equal to 3.0. So x has to be between 1 and 3, and it could also be included in the solution set. So then to graph, we're going to have 0, 1, 2, 3, and 4. We're going to put a closed dot on 1, closed dot on 3, and we shade the space in between them. Okay, the solution set is only in between 1 and 3. So that is what our answer would look like. And just some few extra notes. In this diagram, we have oval A represents some integer solutions of x is greater than 10, or x is less than 10, I apologize, and oval B represents some integer for x is greater than 0. The overlapping region represents the numbers that belong in both ovals. Those numbers are solutions of both x is less than 10 and x is greater than 0. So you can graph the solutions of a compound inequality involving and by using the idea of an overlapping region. The overlapping region is called the intersection and shows the numbers that are solutions of both inequalities. So here would be just the graph of x is less than 10, x is greater than 0. This part that overlaps here in the middle is the graph when you have them together, the and portion. So let's go ahead and look at example 2. We're going to solve inequalities involving and. Okay? So we have 4 is less than or equal to x plus 2, which is less than or equal to 8. So when we do these, we're going to rewrite this as two separate inequalities. So 4 is less than or equal to x plus 2, and x plus 2 is less than or equal to 8. And then you're going to solve both those inequalities, and then that would be part of your solution set. So I'm going to subtract 2 from both sides of my first one. 4 minus 2 is 2. Less than or equal to 2 minus 2 is 0. Left with x. So here x is greater than or equal to 2. And then I'm going to subtract 2 from my second inequality. 2 minus 2 is 0. So I'm left with x. Less than or equal to 8 minus 2 is 6. So we have x is greater than or equal to 2 and x is less than or equal to 6. You can leave them separate like this, or you can create it into one statement. You can have 2 is less than or equal to x, which is less than or equal to 6. So then here you would have to graph it. So we have 0, 2, 4, 6, 8. We're going to have a closed dot on 2 because we have the equal to. Closed dot on 6. And then we shade the region between. So we shade between 2 and 6. And that's what our graph would look like. B, we're going to do the same thing, set up our two inequalities. So negative 5 is less than or equal to 2x plus 3. And then we have 2x plus 3 is less than 9. So to solve the first inequality, I'm going to subtract 3 from both sides. So I get negative 8 is less than or equal to 2x. Divide both sides by 2. Negative 4 is less than or equal to x. 2 divided by 2 gives me 1. So here x is greater than or equal to negative 4. Second inequality, subtract 3 from both sides. 3 minus 3 gives me 0, so I'm left with 2x. Less than 9 minus 3 gives me 6. And then I divide by 2. 2 divided by 2 is 1, so I'm left with 1x. Less than 6 divided by 2 is 3. So now I can combine these two statements. Negative 4 is the lower end, which is less than or equal to x, which is less than 3. So I'm going to now graph this. So I'm going to set up my number line. So I have negative 4, negative 2, 0, 2, 4. Okay. So here at the negative 4, I'm going to have a closed dot. So I'm going to have a closed dot at negative 4. Open dot at 3. So 3 is in between 2 and 4. So closed dot at negative 4, open dot at 3, and then I shade in the middle. So that is what my graph would look like. There are 2 check it out problems for you to try, so go ahead, pause the video, try these 2 on your own, and then resume when you're ready to check your answer. So I have negative 9 is less than x minus 10, and then x minus 10 is less than negative 5. I'm going to add 10 to both sides. So I get 1 is less than x, or I can write that as x is greater than 1. Second one, add 10 to both sides. Minus 10 plus 10 gives me 0, so I'm left with x. which is less than negative 5 plus 10 is 5. Okay? So I can rewrite that as 1 is less than x, which is less than 5. And then to graph it, I'm going to go 0, 2, 4, 6, 8. So in the middle there would be 1. So I have an open dot at 1, open dot at 5, and then I shade in between. So your graph would look like this. For B, I'm going to have negative 4 is less than or equal to 3n plus 5. And then my second inequality, 3n plus 5 is less than 11. For the first one, I'm going to subtract 5 from both sides. Negative 4 minus 5 is negative 9. Less than or equal to 5 minus 5 is 0, so I'm left with 3n. Divide both sides by 3. Negative 9 divided by 3 gives me negative 3. Less than or equal to 3 divided by 3 is 1, so I'm left with n. So n is greater than or equal to negative 3. Second one, I'm going to subtract 5 from both sides. 5 minus 5 gives me 0, so I'm left with 3n. 11 minus 5 is 6. Divide both sides by 3. 3 divided by 3 is 1, so I'm left with n. 6 divided by 3 is 2. So joining those together, negative 3 is less than or equal to n, which is less than 2. So now to set up my number line, I have negative 4, negative 2, 0, 2, 4. So negative 3, close dot. 2 will be an open dot. And then I shade between for the and, because the sections overlap. So those are the answers to the check it out problem. Example 3, we're going to look at a different situation. Here, circle A represents some integer solutions of x is less than 0, and circle B represents some integer solutions of x is greater than 10. The combined shaded regions represents numbers that are outside of either x is less than 0 or x is greater than 10. So here you can graph the solutions of a compound inequality involving OR by using the data of combining the regions. So x is less than 0 is this region over here. X is greater than 10 is over here. When you combine them, you get a left section and a right section, nothing in the middle. Okay? So the combined regions are called the union and show the numbers that are solutions of either inequality. So we're going to have two inequalities to solve, and then we'll graph them. So here, negative 4 plus a is greater than 1, so I'm going to add 4 to both sides. Negative 4 plus 4 gives me 0, so I'm left with a. 1 plus 4 is 5. Second one, I'm going to add 4 to both sides. Negative 4 plus 4 gives me 0, so I'm left with a, which is less than. Negative 3 plus 4 gives me a positive 1. So a is greater than 5, or a is less than 1. So I'm going to go ahead and graph this. So I'm going to have 0, 1, 2, 3, 4, 5. I'm going to have an open dot at 5. A is greater than 5, so I shade to the right. A is less than 1, open dot at 1, shade to the left. So that's what your graph would look like for part A. For B, we're going to do the same thing. Simplify both inequalities. So I'm going to divide both sides by 2. So 2 divided by 2 is 1, so I'm left with x, which is less than or equal to 6 divided by 2 is 3. Second one, I'll divide both sides by 3. 3 divided by 3 is 1, so I'm left with x. 12 divided by 3 is 4. So x is greater than 4. So now I'm going to go ahead and graph. So I have, let's say, 1, 2, 3, 4, 5, and 6. And again, when you do your graphs, your scaling might be a little bit different than mine, and that's fine, as long as your dots are at the right place. They're either open or closed to match, and you're shading the right direction. So x is less than or equal to 3, so I'm going to have a closed dot at 3, and I'm going to shade to the left. X is greater than 4, so open dot at 4, and I shade to the right. So this is what my solution would look like. There are 2 check it out problems for you to try. So go ahead and pause the video and try these on your own, and then resume when you're ready to check your answer. So for A, we have 2 plus r is less than 10, or r plus 5 is greater than 19. So the first one, I'm going to subtract 2 from both sides. 2 minus 2 gives you 0, so you're left with r. Less than 12 minus 2 is 10. Second one, subtract 5 from both sides. 5 minus 5 gives me 0, so I'm left with r. Greater than 19 minus 5 will give you 14. So then we graph our answer. So I'm going to have 9, 10, 11, 12, 13, and 14. I'm going to have an open dot at 10. R is less than, so I shade to the left. Open dot at 14. R is greater than, so I shade to the right. So that is what my graph would look like for A. For B, we have 7x is greater than or equal to 21, or 2x is less than negative 2. For 7x is greater than or equal to 21, I'm going to divide both sides by 7. 7 divided by 7 is 1, so I'm left with x. Greater than or equal to 21 divided by 7 is 3. So x is greater than or equal to 3. The second one, I'll divide both sides by 2. 2 divided by 2 is 1, so I'm left with x. Less than negative 2 divided by 2 is negative 1. So then to graph our solution, we have negative 2, negative 1, 0, 1, 2, 3, 4. X is greater than or equal to 3, so I'm going to have a closed dot at 3, and I'm going to shade to the right. And then the second part, less than negative 1, so I have an open dot at negative 1, shading to the left. So that is what my answer would look like for B. All right, example 4. So every solution of a compound inequality involving and must be a solution of both parts of the compound inequality. If no numbers are solutions of both simple inequalities, then the compound inequality has no solution. The solutions of a compound inequality involving or are not always 2 separate sets of numbers. There may be some numbers that are solutions of both parts of the compound inequality. So now we're going to look at writing a compound inequality from a graph. So for the first one, we see that we have a solid dot at negative 1, shading to the left, solid dot at 7, shading to the right. So here, this is going to be an OR statement. We have x is less than or equal to negative 1. And then the second part, so the OR, we have x is greater than or equal to 7. Okay. Part B, we're going to have an AND statement because this is joining together. This is overlapping the intersection. So we have x is greater than or equal to 0 and x is less than 6. The dot's not filled in, so it's not equal to. So you could write it like this. 0 is less than or equal to x, which is less than 6. So you could write it both ways for that one. There are 2 check it out problems for you to try. So go ahead, pause the video, try these 2 on your own, and then resume to check your answer. So for A, we have x is greater than -9 and x is less than -2. You could write this jointly. You can write -9 is less than x, which is less than -2. So you could write it both ways. The second one, we have x is less than or equal to -3, or x is greater than or equal to 2. So those would be your answers to those 2 examples.